Let's study kernel and image of a homomorphism. And when I say homomorphism without qualification from now on, I mean group homomorphism, because groups are what we are studying. So remember, let's take a homomorphism. Group homomorphism. This already means that G and H are groups, and f is a function such that f of AB equals f of A times f of B for all A, B in G, if you recall. So associated to such a homomorphism, we'll define an important subgroup of H called the image of this homomorphism, and an important subgroup of G called the kernel of the homomorphism. And they control some properties of this homomorphism. So the image has already been defined actually, it's just image as a function. Image of f, it's what we earlier called f of G. Means you take everything in G and apply f to them and see the collection that you get. This is some subset of H, and I have this lemma that we talked about last time. If you look at part A here, it says that if you take any subgroup of G, K, then f of K is a subgroup of H. In particular, G is a subgroup of G, so this image is a subgroup of H. And of course, note that f is onto surjective, means that the image is the whole codomain group, if the image is all of H. This is just a clear observation. There's nothing to prove here. And then the other one is something called the kernel of f. And this is all things in G. So this is a subset of G. The previous one was a subset of H. It's all things in G such that when you apply f to them, you get the identity. I mean the identity of H. So alternatively, you could say this is same as the pre-image of the identity subgroup. And if you look at part B on the right, it says that if you take any subgroup of H, then its pre-image is a subgroup of G. So since this, just the identity, is a subgroup of H, this kernel is a subgroup of G. Okay? This is called the kernel of f. And this is called the image of f. The remark I have here requires a little proving. So let's call this one a lemma, that f is injective if and only if the kernel is just the identity subgroup. The trivial subgroup. We know that it's a subgroup anyway, so it always contains this element. So we're saying that f is injective. You can say whether a homomorphism is injective or not by looking at the kernel. If the kernel just consists of the identity, then you know it's one-to-one, otherwise it's not. Let's prove this before giving some examples. If f is injective, so suppose f is one-to-one. Now since f is a homomorphism, f of the identity is identity. But if it's 1-to-1, then the identity is the only thing that can go to identity. So if x is in the kernel, then f of x is identity equals f of identity. But since f is 1-to-1, f of x equals f of identity implies x equals identity. So that's the easy implication. For the other implications, so suppose that the kernel consists of just the identity. I want to show that f is 1-to-1. How do I show f is 1-to-1? Well, you take a thing called a and a thing called b and assume that they go to the same place when you apply f to them. And then you try to prove that these two guys were the same to begin with. So take a, b in G such that f of a equals f of b. I want to show that a equal to b. And that would prove that different things go to different places when you apply f. The trick is to observe that f of a inverse times b is f of a inverse times f of b, first of all, because it's a homomorphism, and that's same as f of a inverse times f of b. Again, because f is a homomorphism. But then f of a and f of b are the same thing. So it's the inverse of, it's an element times its inverse. So that's identity. Since f of a is f of b. So f of this element is identity means, by the definition of kernel, this element is in the kernel. But the kernel only consists of the identity. Which means this element, a inverse b, is the identity element. And now if you multiply by a on the left, you see that b equals a. So f is 1-to-1. All right. So this is why the kernel plays a rather important role. It lets you decide whether a homomorphism is 1-to-1 or not. The picture that I want you to have in mind is this cartoon. You have a homomorphism, you have the zero element here, sorry, not zero, we call it the identity element here, and you're looking at all the things in G that get squashed to this zero element. That's a subgroup of G that's called the kernel of F. On the other hand, you could take everything in G and apply F to them, and then what you get on the right hand side, this is called the image of F, because it's the shadow of G under F, so to say. All right, let me give some examples. So if you say take some isomorphism, then its image is H. And the kernel is just the identity element, because it's 1-to-1 and onto. That's not very interesting, but that's worth remarking, I think, still. Here is one non-injective, the first non-injective homomorphism that we saw from Z to Z mod n, recall. Be the homomorphism the standard one, takes K to the image of K, sometimes called K mod n, if you remember. The kernel of this is what? It's all the integers that become 0 when you go mod n, and those are exactly the multiples of n. So this is all multiples of n. Let's look at this homomorphism, the determinant map. Remember, that was a homomorphism from n by n matrices with real entries and in non-zero determinant. So these are n by n invertible real matrices. Two non-zero real numbers. The input is a matrix, the output is determinant of that matrix. What is the kernel of this? It's all the matrices that go to the identity. Identity in this group. What is the identity in this group? This is the group of non-zero real numbers under multiplication. So the identity of this group is called 1, the real number 1. So we are looking at all the matrices such that when you apply this homomorphism called the determinant, you get the identity, meaning these are all determinant 1 matrices. That forms a subgroup of GLNR. And you can check directly that this forms a subgroup, but now we see that it's a subgroup because it's kernel of this homomorphism. And you can of course check directly that product of two matrices of determinant 1 is determinant 1, etc. This group is a rather important group. It's called the special linear group, SLNR. That's just a name for it. These are all n by n real matrices with determinant 1. We'll see when we study permutation group next that there exists a rather famous non-trivial homomorphism called the sign homomorphism from the permutation group of n letters to the group of two things plus minus 1 under multiplication. So this is a subgroup of multiplicative real numbers. Yeah. There's this non-trivial homomorphism called sign of a permutation, such that sign of a flip is 1, but the homomorphism is minus 1, I'm sorry. Actually, that determines it. And the kernel of this homomorphism is what is called the set of even permutations. These are set of all permutations that can be written as a product of even number of flips. Flips are transpositions. Flips or transpositions are permutations that in cycle notation look like this. So they switch two things and fix everything else. Turns out that if you can write a permutation as a product of even number of flips, then you cannot ever write it as a product of odd number of flips. And these are rather non-trivial things to prove. What we'll prove is there exists this non-trivial homomorphism, and we'll get this subgroup as kernel of this homomorphism.